with just sitting down?
Yeah.
Okay.
Use your computer.
Yeah. Can people hear me online? I'll go to.
All right, let's press start now.
Yeah.
Yeah. Okay, let's welcome our second speaker, Nancy Aggarwal from Northwestern University. And she will tell us about the gravitational wave unlocking fundamental physics.
Okay, yeah, thank you for inviting me here. Thanks to the speakers, for the organizers to organize this workshop. I'm really excited to learn about all the cosmology that we're going to learn here this week. But this talk will not be about cosmology. This is even more applied than book stuff. So I will talk about one of the detectors that we're building at Northwestern. But just to set some context, it's been 7 years since the first discovery of gravitational waves. And thanks to book, we already explained what gravitational waves are. So I won't do that. I will just give us some context of what have they been useful for so far. So let's take some stock. I've just picked some examples that are my favorite examples. So the first one here is the population of black holes and neutron stars. So in this plot, the vertical axis is the mass of black holes or any compact object, and the blue circles are the black holes that have been observed by the LIGO-VIRGO gravitational wave data. And you can see the purple ones are the electromagnetically observed black holes. And this is a completely different mass population that we did not have access to if we didn't have gravitational waves. So this is good proof that, yes, gravitational waves have been very useful. Similarly, for neutron stars as well, we've seen some very unique events that have taught us a lot about how black holes form. And in fact, we've even seen some black holes being formed in the so-called mass gap, where we didn't really think that black holes existed at those masses. And talking about neutron stars, that's my next favorite gravitational wave event, is when we saw the merger of two neutron stars. We also observed electromagnetic waves from that same event using normal telescopes. And what that allowed us to do was it allowed us to actually understand where heavy metals are formed. It allows us to see these things called kilonovas, which are very violent jets that appear when the neutron stars are colliding. But also, it allowed us to compare the speed of gravitational waves and the speed of electromagnetic waves. And now if you think about that, typically we just assume that electromagnetic waves and gravitational waves travel both at sea, but there are a lot of theories that had predicted that could explain dark matter and dark energy, but they required a little bit of a tweak between these two speeds. So when you have an event like the merger of two neutron stars, which is emitting both gravitational waves and electromagnetic waves, and you can measure those waves here at Earth, you can then compare the speed of those two waves, and then you can start to put constraints on these theories. And that one measurement allowed us to rule out something like 300 theories of dark matter and dark energy. Well, dark matter exists, and we haven't figured out what it is, but it is not modified gravity. Okay, so how do we do that? Well, I'm an instrumentation person. I build detectors. And so just to give you a sense of how what I showed in the previous slide can be done, it's done by building very, very sensitive displacement sensors, or in LIGO's case, you have to build a very sensitive displacement sensor. So this is the noise of the LIGO detector. So the x-axis is frequency, y-axis is the noise in strain. The blue curve is the sum of all the noises in the detector. So if the gravitational wave has a strain that's higher than the blue curve, then LIGO can see it. If it is below the blue curve, we have to do more data analysis tricks to see it. And all the other colors are contributing to that blue curve. So I like to just look at this and think about, okay, the displacement that we're measuring here, the strain that we're measuring here is 10 to the minus 19 per root hertz, or 10 to the minus 20 per root hertz, depending on the frequency. And so the displacement that we're measuring here is that times 4 kilometers. And that's a very small number. In fact, it's smaller than the radius of the proton. So we are observing two giant masses move by a distance that's smaller than the radius of the proton. So we, again, just to think about it, it's like very sensitive measurements that we have to do to look for these gravitational waves. And that goes back to what Wook was saying, that there's G over C to the 4. These are just really small effects. So we have to build very sensitive detectors. So that's the story in the LIGO frequency band. We heard from Wook about LISA and looking for stochastic gravitational waves in the lower frequency bands. There are also pulsar timing arrays that look for even lower frequency gravitational waves. But what I want to talk about today is, can we look for gravitational waves at higher frequencies? And I don't have to convince this audience much, but cosmology-wise, if you want to start cosmology, there's a lot of interesting physics to be done if we could look for gravitational waves at high frequencies. So some of us, we got together and we thought about this question, and we wrote a review article where we've compiled all the proposals that exist, all the detectors that have been built or people have tried to build in the high frequency gravitational waves, and then how far are they from any existing sources of gravitational waves. So in this plot, F is again the frequency. The bars that are dropping down are detectors. So the empty boxes are proposals, and the filled boxes are detectors that have already been built. And the lines in the bottom left are some of the sources that could be in this frequency band. And so here, take this with a grain of salt, because we had to convert a lot of different sensitivities in a lot of different units to all put them on one plot. But I think we've done it right. But there are a lot of assumptions that go into converting those. But basically, this is the picture that there's orders of magnitude between where we would like to be and where we think we can be with any of these technologies. So this is the story of near band stuff. Sorry, that was the cosmological sources. But if you start looking for what I call coherent sources, so now these are late universe sources that are more coherent. For example, mergers of neutron stars or mergers of black holes. Then you're not doing a stochastic search, you can do a coherent search for them. Then the story starts looking a little bit more promising. You know, these same detectors can actually start accessing some of these sources. So in my opinion, we should build them and start looking for these while we research technologies to go down to look for the cosmological sources. So today what I will be talking about is one of these detectors, which is the levitated detector. And that the two most interesting sources for that detector are primordial black holes and superradiance. So this detector is again going to be a higher frequency than what we currently have. It's going to be from 10 kilohertz to 300 kilohertz. So let's, I'll just like give a very quick introduction to what the sources are. So the first source that this detector will be sensitive to is black hole superradiance. So what black hole superradiance is if you have a spinning black hole and its axions exist, then the axions can couple with the angular momentum of the spinning black hole and create a gravitational atom around the black hole. And all these axions can annihilate and emit graviton. And if the axion mass is such that it's at the grand unified theory scale, then the gravitational wave frequency from that axion annihilating will be around 100 kilohertz. So this is why if we want to look for the gut scale axion, then we should build a gravitational wave detector at this hundreds of kilohertz frequency. The second source I said was primordial black hole mergers. So LIGO is of course seeing a lot of black hole mergers, but if the black holes are super light, they merge at frequencies that are higher than the maximum frequency that can be observed by LIGO. And astrophysical black holes cannot be lighter than about a solar mass, give or take. So if we really want to look for unconditional proof of existence of primordial black holes, we should be looking for black holes that are lighter than a solar mass. If you see a black hole merger that's lighter than a solar mass, you see primordial black holes. So now in LIGO, we could see lighter black holes, but the SNR would be lower because we'd be looking at the earlier stages of their spiral where the strain is smaller. So if we can directly look for the merger signal, which is at higher frequencies, then again, we have some access to the dark matter parameter space using that. And then finally, I like to think of this entire field as just sort of exploring the unknowns. Like, we don't really know what's going to be there until we go look. So again, we can have some idea of what we're going to look for, but we might be completely wrong and we might see something completely bizarre. So with that, before I tell you about the detector, I just want to thank the team that I work with. This is a new center at Northwestern. It's called Center for Fundamental Physics, where we build tabletop experiments that look for fundamental physics effects. So this levitated sensor detector, this is again the high frequency gravitational wave detector. The main central point, experimental point that I want to give across here on how the detector works is the idea of optical trapping. So you guys might have heard about optical trapping. It was awarded the Nobel Prize a few years ago. The idea is that you put a particle that has a polarizability, you put it in a laser beam, and it acquires some potential energy from the laser beams. And this potential energy is given by the polarizability times the electric field square with a negative sign. So you see that the particle always wants to move to a position where the electric field is highest. So if you have a laser beam that's focused like a Gaussian beam, then you will have a potential energy profile like this in the radial direction and a potential energy profile like this in the z direction. So the particle would automatically be sitting in a simple harmonic oscillator that's created by its interaction with the laser beam. So this is the case for a traveling beam. Now, if you have a standing wave, then in the z-axis, you can even have like a much stiffer gradient because it's a standing wave. So you have a very high variation of laser intensity at very small distance at the wavelength scale. So then you can build really strong high frequency traps at those. I'm sorry about this. This is unrelated. So that's what we plan to use. So we plan to use an optical trap to build a gravitational wave detector. So the way it works is you have a Fabry-Perot cavity and you put a particle inside the standing wave inside the Fabry-Perot cavity. And again, as I said, the particle likes to go to the place where the field is the maximum. And inside the standing wave, the field would be maximum at the antinode of the wave. So the particle likes to sit at this at the antinode of the blue sine wave here. So now let's think about what does a gravitational wave do to the system. So when a gravitational wave comes by, I'm gonna do this math with you in the frame of the input mirror. Okay, so we're sitting at the input mirror and we're trying to understand what will a gravitational wave do. So the first thing it will do is it will change the length of this cavity. So that's this delta L over here. So it moves the cavity in a way that's proportional to the strain and the length of the cavity. It also moves the particle by the amount of the strain. So the distance between the input mirror and the particle also changes. But what optics tells us is if I change the length of the cavity, then the antinode of the laser moves by an amount that's exactly same as the length of the cavity change. This is just classical optics, this centerpiece over here. And that's the key part, is what the gravitational wave has done now. It has given a relative displacement between the antinode and the physical position of the particle. So if you want to think about it in an undergrad physics level, you should think about you have a harmonic oscillator, and now you've suddenly moved the trap location. And that's what the gravitational wave would do. It has moved the trap location of the particle, and this is that relative motion between the particle and the location of the trap. And this we can see by some simple math is maximized. The signal is maximized if the particle is trapped near the input mirror. So of course we're going to train our detector to be having traps near the input mirror, not like what I've drawn here. And so to think about this, then what this relative displacement does is effectively it's a force on the particle. And the force on the particle will be proportional to the trapped frequency squared, m omega squared, times the displacement, the relative displacement that happened. And now if the gravitational wave frequency was resonant with the trapped frequency, your harmonic oscillator is going to ring up resonantly. And that's why this is, I like to think of this as an optical counterpart of the Weber bar. Weber bar is shown over here in the top left. What these were is just giant pieces of metal waiting there to be rung up by a gravitational wave. And this is very similar. It's an optical cavity, and there's a particle in it trapped, and it's waiting to be rung up by a gravitational wave. So it's an optical Weber bar. Okay. And so now that we understand what a gravitational wave does to that system, we can ask what is the noise in that system? What are the limiting noises that will be the problem in this detector? So fundamental noises, not technical noises. So the fundamental noises in this case are two: gas damping and photon recoil. Gas damping is basically your particle is sitting in a vacuum chamber. There's some gas molecules there. They're hitting the particle and giving it random kicks. So they contribute to a force noise. And similarly, there are some photons from the laser that are hitting the particle and giving it random kicks that are also giving it some noise. So on resonance, if you convert the force noise into strain units, this is what you get. Okay, so here we have some parameters, and in order to make the gravitational wave detector better, we just have to make this noise lower. So we can lower the temperature, we can increase the length, we can lower the recoil heating rate, and we can increase the mass of the particle. In this talk, I want to talk about lowering the recoil heating rate and the mass of the particle, increasing the mass of the particle. So what affects scatter? This recoil heating rate is basically fundamentally coming from photons from the laser getting scattered outside the cavity. So if I draw up the scatter pattern from a spherical particle, which is shown in the left in this left plot, and on the right plot, I am showing the scattered light from a flat particle. Okay, and the laser beam is in the x direction in both of these cases. And what you need to think about is this one is mostly blue, and this one is mostly yellow. Okay, so what that's telling you is that the sphere is scattering in all directions. It's mostly blue, and blue is the max that this color bar goes. And this flat particle is mostly scattering along the direction of the laser, and the rest of the sphere is mostly yellow. So it's not scattering anywhere else, it's mostly scattering along the laser. What that means is that we can actually have a very low recoil rate. We can have a low scattering rate if we go from spheres to flat particles, if we start tracking flat particles. So that's the first message here. The second thing you can do to increase their sensitivity is to increase the mass of the trapped particle. And so for that, we came up with this idea of stacking these flat particles on top of each other and building composite particles. So in order to understand if this thing can be trapped, we have asked some questions, and theoretically it looks like yes, this can be trapped. And so we've done some calculations, and it looks trappable. We've asked all the questions that you would ask if you were trying to trap a new thing, and the answer seems yes, and we're trying that in the lab. So let me quickly just go to the lab part. Oh, sorry, the sensitivity part first. So what that has allowed us to do is, first, we have moved from spheres to disks, and second, we have moved from disks to stacked disks. So we have lower recoil and higher mass. So previously, our sensitivity curve used to be at this dotted line, at the top dotted line, and now we've gotten a factor of 20 improvement by increasing more mass. So this is where our sensitivity will be when we build this thing. And just for order of magnitude, we are sitting at 10 to the minus 22 at 100 kilohertz or something. And then just to superpose that with the expected signals. So this is where you would expect superradiance signals to be if they were coming from 10 kiloparsecs away. And 10 kiloparsecs is roughly the distance to the center of the galaxy. So if you had a lot of spinning black holes in the center of the Milky Way, our final 100-meter detector would be able to see it. And then this is where the primordial black hole signal would lie if you had black holes less than 0.1 solar masses at 1 kiloparsec away. A 10-meter instrument would be able to see it. And all the lighter and further away black holes are under that baseline. Okay, so we've been trapping in the lab. We've been building trapping experiment apparatus in the lab. We have trapped first. This is the first time that anyone has demonstrated trapping of flat objects. So these are little hexagons that you put in the laser beam, and these spectras are all the different modes of these hexagons moving inside the laser beam. And so we've demonstrated that. This is a technical plot, so I'm going to move. And so yeah, so basically what I've told you today, to summarize, we're going to build a Michelson interferometer with a particle trapped right in the center in the each of the cavities over here. And this will help us build a gravitational wave detector that can look for gravitational waves in the frequency of 10 to 300 kilohertz. It is sensitive to superradiance from the center of the galaxy up to 10 kiloparsecs, and it will be sensitive to primordial black holes starting at 1 kiloparsec. And we have started trapping. So stay tuned for the next generation. Yeah.